Now, this is equation number 2 based on the Bernoulli equation. This is equation number 1 based on momentum principle, and this is equation number 2 based on the Bernoulli equation as applied to real fluid flow situation where we have energy loss. Otherwise, Bernoulli equation is stated for the potential flow only, where no loss is there. So, from this equation we can write P2 minus P1, we can manipulate this equation number 2, P2 minus P1 divided by rho is equal to V1 square minus V2 square divided by 2 minus GHL, right. From equation number 1, we have the relationship between P2 minus P1 and in terms of V1 and V2. So, P2 minus P1 divided by rho can be replaced with the help of equation number 1 in terms of V1 and V2, right. Basically, so it means we are interested to develop equation for finding out head loss in terms of velocity, right. So, HL, by manipulating this equation number 2, by substituting the value of P2 over P1 from equation number 1, we will get HL is equal to V1 minus V2 whole square divided by 2G, right. If we want to write in terms of only one velocity, then by invoking the continuity equation, this is continuity equation, Q is equal to V2A2 is equal to V1A1, we can write this equation for HL in terms of velocity at inlet V1 square divided by 2G 1 minus A1 over A2, A1 minus A1 divided by A2 whole square, right. So, with the help of this equation, now we know the velocity at inlet, we know the corresponding areas, we can find out the head loss. So, this is the analytical way for finding out the head loss due to sudden enlargement, right. Similarly, we may have another situation, we may have sudden contraction. So, now let me summarize this derivation, because it is more important than to derive more equation. It is better to understand one than apply the same concept and solve for another situation. We selected control volume, then we applied the momentum equation, then we applied the continuity equation, then we applied the Bernoulli equation at 1 and 2. So, basically we invoked three type of relationship. One is the momentum principle, second is continuity equation, and third is Bernoulli equation. With the help of these three equations, we have got this relationship HL is equal to V1 square divided by 2G 1 minus A1 divided by A2 whole square, right. So, similarly we may have another situation where we have to calculate losses due to sudden contraction. If we need to calculate the losses due to sudden contraction, then let us say we have this figure for sudden contraction. This is the direction of the flow happening in x direction. Here we have a more area, then area is reduced suddenly. If we observe this flow, then this is the pocket where we will have the eddies, and then we have the velocity. So, we select the control volume between 1 1 and 2 2 and apply all the relationship which we have discussed in the just discussed a relationship for getting the formula for head loss in case of sudden enlargement. By the same concept we can find the head loss here also. But practically this loss of energy happens wherever we have sudden enlargement. If we have a contraction, then generally the loss component in contraction is almost negligible. So, in this case what we do, we find out the head loss between section CC. CC is known as basically area, or it is also known as vena contracta, and this is the area where we have the minimum area of the flow passage in the given control volume, right. If we observe these streamlines, then at this point only we have minimum area, right. So, from this section CC to 2 basically we have loss. So, generally the sudden contraction loss is also dealt with the sudden enlargement loss happening between CC and 2 2. So, we can invoke the previous equation and we will apply that one between CC and 2 2, and we can find out the head loss by invoking the previous equations between these two sections at vena contracta and at outlet, right. So, experimentally we have these values also, A2 divided by A1 0, 0.04. If the value of A2 over A1 is equal to these values, then what is the corresponding k, some factor k is equal to this, and with the help of this formula HL, empirical formula, HL is equal to k V2 square divided by 2G. By substituting the value of k in this equation, we can find out the head loss for sudden contraction. So, we have developed these two relationships for calculating the head loss due to sudden enlargement and sudden contraction. We have other type of minor losses also. Suppose we have a bend, fluid is flowing in this manner, we need to change the direction of the flow. Because of the bend also there will be loss, right. So, wherever the velocity changes the direction, there will be some loss, and wherever we have a fittings, like here if we put some valve and this valve is half open, quarter open, 3/4 open, it will have different type of losses.